Okay, so we're ready to start our last section on rational functions. This is going to be 4.6c. What we have done so far is in 4.6a, we learned how to find vertical asymptotes and holes. That's when the denominator was equal to 0. Depending on whether things canceled out, determine whether or not it was a hole or a vertical asymptote. We can find a horizontal asymptote by looking at the leading terms on the top and the bottom, but we can only do that when the degree of the bottom, or the degree of the denominator, is greater than or equal to the degree of the top. What we have not explored is what happens if the degree of the bottom is less than the degree of the top. And here's how I'm going to do this. What I'm going to do is I'm going to step back. I'm going to think back to when we first started doing the horizontal asymptotes. F of x is equal to 2x squared plus 3x minus 4 divided by x squared plus 1. Okay, now a couple of things here should be old hat for you. First of all, there's no vertical asymptotes because this x squared plus 1 is never going to equal 0. You can try and factor that out, but what you're going to get is imaginary numbers. We're only dealing with real numbers when we're dealing with the rational functions because we're graphing them on an xy plane. It's all real numbers. So there's no vertical asymptote and there's no holes. When we look at the leading terms in order to find the horizontal asymptotes, we look at 2x squared and x squared because we're looking at end behavior. So therefore, when x gets very large, we wind up with 2x squared over x squared, which is just 2. So we have a horizontal asymptote at y is equal to 2. As a reminder, do not do horizontal asymptote is equal to 2. Horizontal asymptote at y is equal to 2. So we have an object and we're telling you where it is. It is at y is equal to 2. All right, there's another way to approach this. What we can do is we can actually set it up as it were a division. We can divide the bottom right into the top. X squared plus 1 divided by 2x squared plus 3x minus 4. Okay, divide this in, and here's what we get. We get a 2, multiply it out, we get 2x squared plus 2, 3x, this becomes 0, we wind up with 3x minus 6. Okay, x squared is not going to go into 3x minus 6, so we wound up rewriting our function as f of x is equal to 2 plus our remainder, 3x minus 6, divided by what we were originally dividing by, x squared plus 1. Okay, well, what good did this do us? Well, that 2 should look familiar, and here's our reasoning. If we think about as x goes to infinity, as x gets very large, remember when we're talking about horizontal asymptotes, we're talking about end behavior. X squared is going to get big faster than 3x. That x squared is going to dominate the 3x. So this whole little rational function here is going to have a horizontal asymptote at 0. Okay, so when x gets big, x goes to infinity, f of x is going to approach this 2, that's still there, that's not changing anything, 2 plus this guy is basically going to become 0. It's going to get smaller and smaller. 2 plus 0 is equal to 2. Okay, well, that was just another way of getting our horizontal asymptote. And the question that raises is, why would we want to do this? Because it's so much longer than just looking at the leading terms. And that is true. So when we're looking at when the orders of the top and the bottom are related in such a way to where the degree of the bottom is greater than the degree of the top, it's really not worth dividing that in. Just look at the leading terms. However, when we wind up with the degree of the bottom being less than the degree of the top, that is where we do need to divide it in. So what I'm going to do is I'm going to tweak this a little bit. I'm going to rewrite it. I'm going to change it very slightly. I'm going to make the top, instead of 2x squared, I'm going to make it 2x cubed. And then the 3x, I'm going to make 3x squared. Otherwise, I'm leaving everything else the same. Minus 4 over x squared plus 1. Okay, denominator's still the same. We still don't have a vertical asymptote. We divide this in. We have x squared plus 1 divided into 2x cubed plus 3x squared. We need a placeholder for the x, so plus 0x and minus 4. Okay, we divide this in. We get 2x, multiply it out, we get 2x cubed, and then plus 2x all the way over here. 0, 3x squared minus 2x minus 4. All right, x squared goes into that 3 times, so plus 3. 3x squared plus 3. And what we are left with is 0 minus 2x minus 7. Okay, so when we divide that out, what we wind up with is our function is equal to this 2x plus 3, and then plus our remainder, which is negative 2x minus 7, divided by x squared plus 1. Okay. Well, here's what happens. As x gets very, very big, let's see what happens. 2x is not going to go away. That's just going to remain 2x. It's going to look like a line. 3, that's not going anywhere. This expression here, the power of the bottom is greater than the power of the top, so that's going to approach 0. So what we're left with is, as x approaches infinity, g of x is going to approach 2x plus 3. That's not a number. It's going to approach a line with slope 2 and y-intercept 3. Let's take a look at this. I've got these already plugged into the calculator to save a little time. First, let's look at our first example. I've got it listed here as y1 and y2. The 2x squared plus 3x minus 4 over x squared plus 1. This is the one with the y, or the horizontal asymptote at y is equal to 2. Here comes our rational function. No vertical asymptotes, as you can see. There goes our horizontal asymptote. So we were right in our prediction. Okay, cool. I'm going to go ahead and silence those. Now I'm going to do the 2x cubed plus 3x squared minus 4, the one that we just divided out. And I'm also going to plot 2x plus 3, which is what we hypothesized to be the asymptote. When we graph this, here comes our rational function. No vertical asymptote, but as you can see, we have an asymptote, but an asymptotic behavior, but it's not horizontal. We don't have a line that's going from left to right, right to left, horizontally. We actually have a line that is coming up with a slope of 2 and a y-intercept of 3. And as our function, as our x values get bigger, our function gets very, very, very close to that. All right? The term for this is called a slant asymptote. Why? Because it's an asymptote and it's slanted. So what we are left with is this little strategery for finding our asymptotes. The vertical asymptote and holes, that's when the bottom is 0. Okay? Our horizontal asymptote, we look at the leading terms, and we can only do that when the degree of the bottom is greater than or equal to the degree of the top. Okay, so this little section here looks a whole lot like what I did right at the beginning of the little blurb here. Now, finally, our last section, slant asymptotes, or SA. What we have to do here, well, first of all, when we look for slant asymptotes is when the degree of the bottom is less than the degree of the top. And what happens there is we have to divide the bottom into the top. So actually execute the division. Okay? When we execute that division, we're going to be left with a function, and we're also going to have a remainder. And that remainder, when it's divided by the denominator of our function, is going to basically go to 0, just like what's happened each of these times. And what we're left with is the 2x plus 3 in this case, or in the case if you want to, if you're a glutton for punishment, you actually want to divide it all the way out. When you've got a horizontal asymptote, you'll just have the 2 and have a horizontal asymptote. So when in doubt, you can always divide it in. Now, now that I've done that, I have to let you in on a little secret. When we first looked at asymptotes, I defined the asymptotes as a line that the graph approaches. That was only semi-true. Not the graph approaches part, that's fine. The part that actually is a little wishy-washy there is the line part. Let me show you an example. What I'm going to do is I'm going to tweak that same function again. I'm going to make the leading term 2x to the 4th on the top. Everything else is the same. Plus 3x squared minus 4 divided by x squared plus 1. Okay, now we know. When we look at, first of all, if we want to find vertical asymptotes, we don't have any because this denominator is never going to be equal to 0, so no vertical asymptotes. Then we look at the degrees of the top and the bottom. The degree of the top is greater than the degree of the bottom, so therefore we can't just look at the leading terms. What we have to do is actually divide it in. X squared plus 1 going into 2x to the 4th. We need a placeholder for the cube, so plus 0x cubed plus 3x squared. We need a placeholder for the x, so plus 0x, and then minus 4. All right, divide this in. We get 2x squared up here. Multiply it out, we get 2x to the 4th plus 2x squared. You get 0. 0 minus 0 is a whole lot of 0. 3x squared minus 2x squared is x squared. Nothing from the 0x and minus 4. All right, x squared plus 1 into x squared minus 4. We get plus 1 multiplied out. We get x squared plus 1 down on the bottom, 0, and minus 5. So when we write this out, we get our function is actually equal to 2x squared plus 1 minus 5 divided by x squared plus 1. Okay, let's see. Apply the same rules. As x goes to infinity, as x gets really big, 2x squared is not going to go away. 1 is not going to go away. It's not going to matter so much, but it's not going to go away. And then this last term, 5 over x squared plus 1, or I should say negative 5 over x squared plus 1, that's going to approach 0 because x squared plus 1 is going to get a whole heck of a lot bigger than 5. So g of x is actually going to approach 2x squared plus 1. So when we graph that, let's see what happens. I'm going to silence the other two graphs that we were just looking at. And here we go. y5, 2x to the 4th plus 3x squared minus 4 over x squared plus 1. So we want to look at that. And then 2x squared plus 1. When we graph that, here's our function, our rational function, coming down from above and then zipping back up again. And here's 2x squared plus 1. It's a parabola. So instead of having a linear asymptote, which is a slanted line or a horizontal line or something like that, we actually have a parabolic asymptote. Our function, which is down here on the bottom, as x gets larger, it seems to Get closer and closer and closer and closer to that parabola. Now, a quick and dirty trick to just see if something has a slant asymptote or a parabolic asymptote is that you actually can still look at your leading terms just to get the gist of what it might look like. It's not going to be very detailed, but just to get the gist of what it might look like. You got x squared on the bottom, you got 2x to the fourth on the top. 2x to the fourth divided by x squared is 2x squared. That's where that came from. So you do miss this y-intercept at 1, but it does give you a rough idea of going, oh, hey, it's going to be second order. I'm going to have a parabolic asymptote. If I apply the same line of thinking to my slanted asymptote that we just did, we look at 2x cubed, we look at x squared, we divide them, we get 2x. So I get the 2x. I'm missing the 3. So it does not give me the whole picture, but it does give me a quick idea. So you can look at that and say, oh, it's going to be a slant asymptote. Will it automatically give me exactly what that slant asymptote is? No, but it is kind of a quick shortcut for just getting a little bit of information. However, if you want to get the actual asymptote, you have to divide it. I know it would be really seductive to be able to just look at your leading terms, but you got to divide it, I'm afraid. All right, here's your practice. What I want you to do is, this is section 4.6. I want you to get all of the asymptotes, and this may be redundant with something you've already done, but all of the asymptotes for number 15 and number 21. Not surprisingly, they're probably not going to be horizontal asymptotes. One of them is a slant asymptote. The other one's a little bit of a surprise. Good luck, and I will see you in class.